Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Starting material is 4-chlorotoluene, Cl at C4 CH3 at C1. The product has CO2H at C1, where CH3 was, Br at C5, adjacent to Cl, number 2 at C2, ortho to CO2H, and Cl at C4, unchanged. So we need to introduce Br onto the ring, oxidize CH3 to CO2H, and nitrate the ring. Moving on to the next step. The CH3 group is an ortho-para director. Cl is also an ortho-para director. In 4-chlorotoluene, both groups cooperate to direct incoming electrophiles to specific positions. Bromination with Br to Fe-Br3 on 4-chlorotoluene, CH3, at C1 directs ortho-para and Cl at C4 directs ortho-para. The position between Cl and CH3, i.e., C3 and C5, is activated by both groups cooperatively. Bromination occurs preferentially at C3 or equivalently C5, ortho to Cl and meta to CH3, but since the molecule is symmetric about the Cl-CH3 axis, position ortho to Cl is equal to C3 or C5. Given the product shows Br at C5, ortho to Cl at C4 and meta to CO2H at C1, bromination first with Br to Fe-Br3 places Br ortho to Cl, the ring position activated by both Cl ortho-para direction and CH3 ortho-para direction cooperate at C3-C5. Moving on to the next step. After bromination, oxidize CH3 to CO2H using KMnO4 and heat. This converts the methyl group to carboxylic acid without affecting the ring substituents. And for the final step. Now the ring has CO2H, deactivating, meta-director, Cl, weakly ortho-para, and Br, weakly ortho-para, at C4 and C5. Nitration with HNO3H to SO4 introduces number 2. The CO2H group directs meta to C4 area, but Cl and Br direct ortho-para. The combined directing effects place number 2 at C2, ortho to CO2H is not favored by CO2H, but considering Cl at C4 and Br at C5 position C2 is ortho to CO2H, meta to Cl, the position activated by the halogen directors. In the product, number 2 is at C2, ortho to CO2H at C1 meta to Cl at C4, which is consistent with direction by the halogen substituents. Br to Fe-Br3 first, while CH3 is still activating and directing, ensuring correct Br placement, then KMnO4 oxidation, then nitration. This sequence is optimal. Option B. KMnO4 first converts CH3 to CO2H, making the ring deactivated before bromination, making electrophilic bromination difficult and giving wrong regiochemistry for Br. Option C. NBS in CCl4 is a benzylic bromination reagent, free radical, which would brominate the CH3 group, benzylic position, rather than the ring, giving benzyl bromide not ring-brominated product. Option D. NBS gives benzylic bromination, then nano to heat is not a standard nitration procedure for aromatic rings. Therefore, the correct answer is A. Therefore, the correct answer is option A.